All right, let's go ahead and practice the skeletal method on drawing some more Lewis structures. So let's go ahead and start with HCN. So let's go ahead and start by figuring out how many valence electrons we have. Well, hydrogen has 1, carbon has 4, nitrogen has 5, so we have a total of 10 valence electrons. So as we draw our skeleton, this is a structural formula, so we have HCN. Okay, so as we look at this, we'll go ahead and draw our single bonds in first, so 2, 4. So we're down to 6 valence electrons. And now we need to complete the octet on the terminal atom. Well, we can't do that for hydrogen, and nitrogen is more electronegative anyway, so we'll go ahead and complete the octet for nitrogen, which uses up the rest of our valence electrons. All right, so let's check. Does everything obey the octet rule or have filled outer orbitals? So hydrogen does, and nitrogen does, but carbon does not. So carbon does not obey the octet rule. So what I would do is go ahead and look at the formal charges. So carbon is supposed to have 4 valence electrons, but remember the bonds only count as 1 apiece for formal charge. So carbon has a +2 formal charge. Nitrogen is supposed to have 5 valence electrons, but then for here, it has a -2 formal charge. So what we're going to do is to minimize the charge, we're actually going to have to move 2 lone pairs in. And then we'll get this as our end Lewis structure. So we'll have HCN, and there's a triple bond. Okay, so now carbon and nitrogen both obey the octet rule. They have 0 formal charge, and then hydrogen has that single bond as well. Okay, so as we move on to CO2, let's figure out how many valence electrons we're supposed to have. So carbon has 4, each oxygen has 6, so that's a total of 16 valence electrons. We talked previously that if possible we need to have a symmetric skeleton, so we'll have O, C, O. We'll add our 2 single bonds, 2, 4, so we're down to 12 valence electrons. So now we need to fill up the octets on the terminal atom, so we'll have 2, 4, 6, 2, 4, 6. So that gets rid of all of our valence electrons. So this is symmetric, but carbon does not obey the octet rule. So let's go ahead and figure out if we have any formal charges. So the Lewis symbol for oxygen is supposed to have 6 electrons, but right now it has 7. So each oxygen atom is equivalent. So each one has a -1 formal charge. Carbon has a +2 formal charge. So to minimize these formal charges, you're going to have to move a lone pair in from each oxygen to obtain this structure here, where everything obeys the octet rule and has 0 formal charge. All right, as we look at CH3OH, how many valence electrons do we have? Well, carbon has 4, and then we have 4 hydrogens, each with 1, so that's a total of 8, plus oxygen has 6, that's a total of 14 valence electrons. So the skeleton, we have carbon, we have 3 hydrogen atoms bonded to that. Then we have oxygen, and then we have hydrogen. So we go through, we add single bonds first, so 2, 4, 6, 8, 10 valence electrons have been used up. So we have 4 remaining. We can't put any of the valence electrons on hydrogen, so it's between carbon and oxygen now. So carbon has a completed octet, but we would add it to oxygen first anyway, because oxygen is more electronegative. So oxygen can take on another 2 lone pairs for a total of 4 valence electrons. So now everything obeys the octet rule, and nothing has a formal charge on it. They all have a formal charge of 0. Let's go ahead and go to our next example of ethanol. We have CH3, CH2OH. So we have 2 carbons, each with 4. So that's a total of 8. Plus we have a total of 6 hydrogens, each with 1, so that's 14, plus the oxygen is a total of 20 valence electrons. If we were to draw out our skeleton, we have CH3, CH2, OH. So the first thing we'll do is we'll go through and add single bonds first and take away 2 valence electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons used up. So we have 4 remaining. All the carbons obey the octet rule. The hydrogens are in good shape. The oxygen doesn't obey the octet rule. So we're going to need to add those lone pairs there. So now everything obeys the octet rule. There's no formal charge, so there we go. We have a good Lewis structure. All right. Let's go to this one now. We have H3PO4. So let's start by figuring out how many valence electrons we have. Well, we have 3 from the hydrogens plus 5 from phosphorus. That's a total of 8. Then we have 4 oxygens, each with 6. So we have 24 from the oxygens plus 8, so we have a total of 32 valence electrons. So how are we going to draw this structure? Okay, well, there's 2 different acceptable structures for this, but there's only one acceptable skeleton. So if we were to start out by drawing this, we would probably choose phosphorus first. And then if you were going with the same logic as before, like CH3OH or something, you'd probably say, well, there's going to be 3 hydrogen atoms around the phosphorus, and then maybe there might be 4 oxygen atoms. Okay, so this does not look like a very symmetric Lewis structure, and we want this to be as symmetric as possible. In fact, this one kind of looks like that. So what we want to do is this. To make this a symmetric Lewis structure, we are going to go ahead and put phosphorus as our central atom. But then, to make this symmetric, we know that the hydrogens have to be terminal atoms. So what I would do is I would put my 4 oxygen atoms around phosphorus and then put hydrogen off of 3 of them. So now I would go through and add my single bonds. So 2, 4, 6, 8, 10, 12, 14 valence electrons have been used up. So we're down to 18. Then you'd have to complete the octet on this oxygen without the hydrogen first, because it's a terminal atom. All of the other oxygens are central atoms because they're bonded to 2 or more things. So we'd complete this octet first, so 2, 4, 6. That takes us down to 12 valence electrons. Now we need to add valence electrons to the remaining oxygens. Okay, so that's 12 valence electrons. So we've used up all of our valence electrons. So now, this is where we have to make a choice. If we look at this, right now everything obeys the octet rule. Okay, hydrogen has that single bond, which is good, but all the oxygens and the phosphorus atom all obey the octet rule. But if we look at this a little more closely, what we'll see is there's some formal charges. The oxygen up here, the terminal oxygen, has a formal charge of -1. And then phosphorus has a formal charge of +1. So if we were looking for a Lewis structure to obey the octet rule, this would be an acceptable structure. If we were looking for a Lewis structure that minimized formal charge, we'd have to move a lone pair in from this Lewis structure here. And what we'd end up getting there is something that looks like this. Okay, so here, the phosphorus doesn't obey the octet rule, but there's 0 formal charge on everything. So what actually exists? It's probably a combination of the two, but you would need to read a question on an exam, and then I might say which Lewis structure would most likely exist if the octet rule were followed or if formal charge was minimized. So just make sure you're being careful as you read through that. All right, let's try a few more examples. So we have a poisonous gas here used as a fumigant and rocket propellant, cyanogen, C2N2. So as we look at this, let's go ahead and start out by figuring out how many valence electrons we have. Well, each carbon has 4, so that's 8, plus 10 from the 2 nitrogens, so we have a total of 18. So the question is, does our skeleton look like this, CCNN, or does it look like this? So I would go with the second option because it's more symmetric. All right, so let's go ahead and start by adding single bonds. So we'll have 2, 4, 6. So we're down to 12 valence electrons. So what we need to do now is we need to complete the octet on the terminal atoms. So that takes us down to 6 after completing that nitrogen. And after completing this nitrogen, we've used up all of our valence electrons. So as we look at this, you should be able to see that both of the nitrogens obey the octet rule. The carbons do not. So now we need to go through and assign some formal charges. So the formal charge on each nitrogen, -2. The formal charge on each carbon is +2. So in order to minimize these, you can go through in a stepwise motion. So I'm going to move one in from each side first. So you'd have something that looks like this. But as we look at this Lewis structure, you'll see again, the nitrogens obey the octet rule, but the carbons do not. And whenever you go through and assign formal charges, the terminal nitrogens have a -1 charge. Those carbons have a +1 formal charge. So we'll need to move in yet another lone pair. So we'll end up with a Lewis structure that looks like this. So now everything obeys the octet rule. There's no formal charge. So we're all done with this Lewis structure. All right, so next time what we'll do is we'll start our discussion on resonance and talk about how we can have multiple structures to give us a good description of what's actually occurring.